Okay, so today we're going to take a look at deriving acceleration without using any without using any quantities. We're using variables only. And so we're going to do the force toolkit here. And the first thing we're going to do is going to choose our system. And so whenever you have a two-block system or two-body system, you should start off finding the acceleration by finding the acceleration of the whole system. So our system is going to be block A and block B. The second thing we're going to do is we're going to choose our axis. And usually I like to choose the axis of direction. And so going up the hill and over the pulley, that whole axis is going to be the axis of direction. You'll see how that works in a moment. And that's going to be positive to the right. The third thing we're going to do is we're going to draw our free body diagrams, and I'll draw one for A and one for B. Okay, and so as we go through here, start off by drawing the forces on them. And so the force of tension is going up the hill right here, and so that would be the force of tension going up the hill. And this block has the force of gravity down and a force of gravity up. And so the reason this block is going to be moving this way, and this block is actually, it could be bigger or smaller than this block, but in most of the questions we have online, this block is bigger. And so being heavier, the block is going to accelerate in that direction along this line of your axis of acceleration. So this force of gravity is this force of gravity, FGB, and the force of tension is FTB, and this force of tension here is FTA. Okay, this block is going to have a force of gravity straight down on it, and it will also have a force of friction going against it. And since it's moving, that will be FK. And then, of course, it is also going to have a normal force straight up. And so we got our normal force, our force of gravity, our force of friction. And these are all the forces shown in these two pictures right here. FGY and FGX are our components that we're going to worry about in a moment here. So let's take a look at the next step. So the next step is to write the sum of the forces equals mass times acceleration. But before I do that, which I'm going to do in a moment down here, before I do that, I want to define all my vector arrows here. And so we can kind of see what's going on. So FGA. So FGA is the force of gravity going straight down, and that is MA, mass A, times gravity. FTA and FTB are the same thing. So FTA is going to be equal to FTB because this is a string. It's a continuous string, and the tension along the string is the same at any point along the string. Moving over to B, FGB is going down, so that is the mass of B times G, and FTB is going up, and FTB is equal to FTA. Now you could talk about positives and negatives, but we'll talk about that later when we show putting them all together into the equation. Moving on, the force of gravity components. As you see here, I have a force of gravity that is going down the hill in the same line as the friction, in the same line as the hill, and that is going to be my FGX. And so FGX is going to be the sine of this hypotenuse. And so FGX is going to be defined as the mass of A times gravity times sine theta. And then FGY is going to be the opposite of the normal force, but we'll get to that in a second. And FGY is next to, adjacent to theta. So FGY will be mass of A times gravity times cosine theta. Continuing on, since Fn is the opposite of FGY, then we can say that FGY and Fn are going to be equal and opposite. They're going to balance each other out. Their net force will be 0 in this direction. So that says Fn is equal to Fgy. Fk is always defined as mu sub k, which is the coefficient of kinetic friction, times Fn. So therefore, Fk is going to be mu sub k times Fn. Fn is equal to Fgy, and Fgy is mass of A times g cosine theta. So literally this is Fk is equal to mu sub k times the normal force, which is equal to the force of gravity in the y direction. Okay, so now we've defined pretty much everything in our force diagrams, in our free body diagrams. So now what I want to do is I want to go back to making a statement about the net force being mass times acceleration. In the y-axis, which this is the only part that's off axis right here, this would be my y, right? If my y is along this axis here, that's the only part that is not in this plane of motion. So the plane of motion goes up and it follows the string. So I'm going to call that my x-axis. There's nothing out of the x-axis here, side to side, so I don't need to worry about that. There's no side-by-side motion. Here, this is not in my direction of motion, so these will cancel out. So going down here, in the y-axis, Fn minus Fgy equals 0, and it's not going to bounce up and down off the hill. My x-axis, however, I'm going to add up all the forces to the right along the line of action, minus the forces to the left. And so looking at this, just thinking about this, why is this moving over the hill? Well, this block B is heavier than block A. And so block B is going to drag this thing over the hill. So this is the force that's pulling things down. And then I have the tension here. These two will actually cancel each other out, FTB and FTA, right? But FTA is going that way, FTB is going that way, so let's account for it in a moment. And then I have two forces acting against it on the hill. I have the force of friction, and I have the x component of gravity, which is Fgx. So those are things working for and against the item as it's going, the system as it's going to the right. So my sum of my forces equals mass times acceleration is the force of gravity of B pulling down minus the force of tension on B plus the force of tension on A, which is pulling it up, minus the force of kinetic friction minus the force of gravity in the x direction equals m times a. Remember, we're doing it with our system, so it's both blocks, ma and b, mb. The tension here cancels. If this is a million minus a million or a negative million plus a million, it doesn't really matter. They cancel, so we'll just get rid of them right now. Bam, bam, gone. Fgb is the mass of B times gravity minus Fk. We said Fk was the mu sub k times Fn times the normal force. That's the force of friction minus the force of gravity in the x direction. And these are both negative. They are down the hill in the leftward direction. This one is over the pulley to the rightward direction, so it's positive. And of course, ma plus mb times a. Now we're solving for a, right? So all I got to do is mathematically rearrange this to say that acceleration will be equal to the force of that block pulling over the edge minus the force of friction pulling it back minus the force of gravity in the x direction, or the x component, over the combined masses. And that's a really good way to look at the acceleration because all the forces are all lined up and kind of derived. I can further derive this by saying this g and this g and this g are all the same thing, so I can distribute it out just to make my math a little easier. And it's a little cleaner right here is my final answer. Okay, then the second part of the question is to derive T, tension. So I'm going to choose the right side instead of the left side to derive, because I could find T here, but then I got to deal with Fgx and Fk. You know, just easier, cleaner to do this one, right? Super simple. So now I'm looking just at the object B. And so before, my system was going to be the whole thing, and now my system is just block B. So just looking at block B, I had the force of tension going that way, and I had the force of gravity going down. And so this is the force of gravity going down, and this is the force of tension pulling up. And remember how we've defined this, so that down along the pulley is going to be positive. So that's why that's negative equals ma. I rearrange this, and I solve for FTB. FTB equals mb times gravity minus mb times acceleration. I distribute out the MB, and I get FTB equals massive B times the quantity, gravity minus acceleration. Now, acceleration I already got above. It's this whole darn thing. So now I drop the whole darn thing in there, and I get my derived form of FTB. Now, what do I do? Now, I'm going to go to the quiz. And the quiz here is going to give me some values. What values is it going to give me? All the values I need to solve this. So it's going to give me the mass of A, the mass of B, the coefficient of kinetic friction. Careful, because it probably already also gives you the coefficient of static friction, but since it's moving, you don't want to use that one. Don't get caught. And then it'll also give you theta. Does it work? I don't know. Plug it into your equations right there. Boom. And on your second one, you don't have to plug it in all over again, do you? Right? Because you can just do this. Because on your second one, you're already going to have A. You know, you can put A right there. You're going to put A right there. That's going to be A. And this is going to be FT. And just see if it works. You know, plug it into your equations and see if they work. And you need to be able to do this for the exam. You know, can you do this on your own? So I just did it, right? But can you do it on your own? Maybe take a different one. Maybe take the one that looks like this and see if you can derive A, right? This is the one that's sitting on the cabinet like this. And you got block A and block B, where this is block A and this is block B, right? Can you derive? So you're going to have to do some deriving on the test as well as solving on the test. So anyways, hope you enjoyed that. That was a lot of fun for me. So I will see you guys later.